Okay. Yeah, I hesitated to make this video because there's so many out there on YouTube land. How to graph rational functions. But considering that we're struggling, a lot of folks aren't looking at these enough and you got a final exam coming up. I thought I would make a video where I'm going to break it up into probably 2 or 3 parts. I'm guessing. I don't. Part 1 is just going to be, what are you looking at? And what can you say about the graph just by looking at it in your first 10, 20 seconds of consideration as to what's this graph look like? How do you get started? That's more simply put. How to get started? Well, the first thing is we've got to talk about fractions, because rational numbers are really these equations. And I've got 5 of them, I guess. And I'm going to look at this as to what are the immediate things you can say just from the way they are currently written. Eventually, we'll need to factor these to get a better sense of what's going on. But right now, we're just looking at fractions. And so when I put numbers in for x, as I evaluate these fractions given certain x values, and we're going to use user-friendly numbers for the most part, what can I say? Well, let's talk about fractions in general. When you describe numbers, I hope that you've heard it enough this semester that positive, negative, or zero, or undefined. So you can have positive numbers, you can have negative numbers, you can have fractions that equal 0, you can have fractions that are undefined. Next, big or small. You can have fractions that are big. You can have fractions that are small. And generally speaking, when we graph these calculations, we get all of those things for the most part. The undefined situations sometimes preclude us getting certain fractional values, but generally speaking, you're going to get all of these things. All right, and so let's start with just y equals 1 over x, and let's see what we can find out. And one thing for certain, that if you want to understand functions, you got to play with numbers. At some point, you got to do some computation. All right. Having said that, how would I get 1 over x equals 0? What number would I plug in? You can't. Division becomes multiplication. You can move the x to the other side. X times 0 is 0. Gotta get my eraser. I had it there a second ago. Here it is. And please write to me if you think that is true. Okay. 1 divided by 0 then is what? Sure looks like it's undefined. Okay, so can I make this fraction equal 1? Sure, if I let x equal 0, then at x equals 0, I'm not getting a y value. For right now, let's just put a little dotted line, pretending we're a computer, searching out the y value, we don't find one. All right, well, when is 1 over x going to be small? Let's find out. When is 1 over x going to be small? Well, let's see. Let's put 1 over 1 in. Oh, we'll call this 1. Looks like we get 1 out. How about 1 over 10? Whoa, that didn't take long. Looks like we got a small fraction over here. That's 1. Let's call this 10. Let's call that 1 over 10. All right, well, that's a start. And what happens if I put a 0? Another 0. What's even smaller? Sure looks like I can immediately look at this the next time and go, oh, that's going to 0. If I look at this function again, and I've had this conversation, I should know that that's going to 0. And we're going to establish patterns here in this part 1 video as to when it doesn't go to 0. How do we know? Hopefully by the end of part 1, when we get to that last function, that 5th one, you'll have at least a better chance of understanding that, or at least you're starting to consider it, and with future considerations, the light bulb goes on. All right, I'm not talking about it too much yet. Back to this. Let's look at it from a graphical standpoint. 1, I put a dotted line here, y equals 1. That's a constant. I don't care what x, I give you, this function gives you a 1. Okay. Now, y equals x, hopefully we're familiar with that. That seems to be getting bigger and bigger and bigger and bigger. Ah, what did we say happens when a number gets bigger and bigger and bigger, and we try to plug it in underneath the number 1? We just did it a little while ago. Remember, we finished with 1 over 100. We start getting small. So from a graphical standpoint, I can see that this amount, we'll call it y2. The numerator, we'll call it y2 for the moment. y1 at this amount gives us that. That's y1. This is y2. Oh, geez. y2 divided by this big number doesn't seem to fit into this. No, not at all. And the bigger this gets, the fewer times it fits into this. Okay, so we can make fractions really, really small by making the denominator much bigger than the numerator. Now, how do we make a number really, really big? We make the denominator really, really small. Really, really small number. So let's make it 0.01. How many times does 1 divided, what is 1 divided by 0.01? What is 1 divided by 100? I think that goes in 100 times. Right? Division by 1 over 100 is the same as multiplying by 1 over 100. And I hope you can see they're equal. That's a different way of saying that. And what happens if all of a sudden I put another 0 in there? Then I've got 1 divided by 1 over 1,000. I hope you immediately say that goes in 1,000 times. How can we see it graphically? Well, as I let y equals x go to 0 from the right, it's basically what I was talking about over there. These numbers get smaller and smaller. These y values get smaller and smaller and smaller. It's kind of like adding zeros. That y value gets smaller and smaller and smaller, and the fraction gets bigger and bigger and bigger, and I don't know how many zeros I drew, so I'm just going to erase it. So, how do I get close to 0? Ooh, I pick an x value, and we said it goes in lots and lots of times, and we're off and running. Y equals 1 over x looks something like that, and I could have done the same thing with negative numbers. I'm not going to beleaguer the point. So I can see that immediately. So what can I see? 1 over x. When I look at that function, I look at it and I go, there's no way I can make it equal 0, because the only way I can make a fraction equal 0 is to make the numerator equal 0. And without a variable, I'm up the creek. What else can I see immediately? Well, if there's no x, if I can't pick 0, then I'm not getting a y-intercept. I think we can validate that with what we've done already. And I can see this as this gets bigger and bigger and bigger, my fraction's going to 0. So that's what I would say immediately. We won't be coming back to this one. All right, we will eventually write some limits. We'll eventually put some limit notation on the board, but that will probably come in part 2 or part 3 of this little video. All right, so new function. Make sure I can see that properly, or you can. Yep. Hope the red is showing well enough. X minus 2 over x plus 3. So what can I immediately see? Not immediately see. 0 gets me negative 2/3. I'm not going to hesitate. I'm just going to take it. If I plug in 0, get rid of the variables. Okay, I got a fraction. What else can I immediately see? I can immediately see that. What makes that 0? Talked about it just 5 seconds ago. Maybe a minute. 2. If I plug in a 2, I get 0 over 5, and I know that fraction equals 0. So 2, x-intercept. Immediately, I take it. What can I immediately see? Besides that, the end behavior. The end behavior, what's going to happen? Well, let's take another closer look at x minus 2 over x plus 3. You can pause the video. What else can you say about that fraction? If you plug in numbers, what happens? The numerator is going to be 5 less than the denominator. Now, I had originally changed this because I thought it would be easier for you to look at x plus 3, so I'm gonna do that. X minus 2. Okay, so that's gonna change something. What's it change? Changes our y-intercept. No longer 0, negative 2/3. It didn't hurt to actually do this, so you get a little rep. So now I'm looking at negative 3. Gets me a 0, and 0 gets me minus 1.5, minus 3/2. Okay, hopefully I position those in a way that won't interfere with what we're looking at. All right, what else do we know? Well, my numerator and denominator are 5 apart. So let's get something, let's put in 102. I put in 102, I get 105 over 100. 102 is what I mean by end behavior. I'm putting in some big numbers, get a feel for the calculation. Once again, if you have trouble with any graph, plug in numbers. You plug in enough numbers, you're going to learn something about the trajectory of the functions that you're studying. So I can see that, let's put in instead of 100, let's put in 1,000. I put in 1,000, I get 1,005 over 1,000. You know what? I think that's pretty close to 1. I hope you can see that too. So that's my end behavior. Putting in big numbers, you get the end behavior. So y equals 1. So that's what I see here before I do any other work. Immediately see that. And what else can I see? One last thing. We already used negative 3. It's critical to this problem. So is positive 2. What happens if I put positive 2 in? I get 5 divided by 0. And I hope you're starting to realize that that is undefined. So what number did I plug in? 2. Let's plug in a 2. Let's say that it's 1.5, 2. Let's call it there. Let's try to do some justice to this by not squishing up that y-intercept. All right. All right, so I'm beginning to see the pattern here, but we'll come back and put some more numbers in, because this is all about what can I do before I dive in more deeply into the process of graphing this. So now I got another one. This is the one I just did. Now we're looking at x minus 2 over x squared minus 25. What can I see immediately? Well, immediately, see, I can see that this is too far away. So I'll get that over here. Y-intercept. I can immediately see the y-intercept. Hand over the variables. 2/25 positive. 0 gets me 2/25. Okay. I can immediately see that 2 gets me 0. I can immediately see, well, I can see plus or minus 5, but from the standpoint of what you can see before you factor, and many of you might be factoring that in a moment, I hope you can just see the plus minus square root of 25. Okay, but I can definitely see the end behavior. All right, so if I put something really, really big in, and we'll do it, we'll do that. But I also have a graphical look at it. I've got basically an x squared function in the denominator, a linear function y equals x in the numerator, and I get a feeling for the y values, like the y value of x to the 1, right? It's different than over here, our last function, both numerator and denominator's biggest term was x to the 1. This one's bigger. So when I put a number in, let's put 10 in. I get 10 over 100. Let's put 100 in. I get that to be 1 over 4 zeros. Right? Now I'm doubling the zeros each time. So let's do 3 zeros. It's going to give me 6. Okay, and I hope everybody knows how to do the cancellation here, right? This one. Right? So this is 1 over 100. This one is, get rid of 2, 1 over 100. I did something wrong. This one had 1 less zero than it should have had. So this is over 1 over 1,000. This is 1 over 100, and this one is 1 over 10. And you look at those fractions. All right, this is the smallest one. So where is this really headed? It's headed to zero. This X value. I get that Y value. I get one that's huge for a second Y value. This one is not going to fit into this. And this one here, they're the same. So there's a point there where I can find an X where they're equal to each other. And maybe we'll find them. So I can see that this thing is going to zero. And if I put negatives in, still goes to zero. The question is, from which direction? We'll study that in more detail in part 2. But right now, remember the focus of this is to get an idea of some patterns, some quick patterns that emanate from the exponential activity that you're looking at. So let's try our fourth function here. And you can pause the video and see if you can name the things that I'm about to name. What can I see? See -8 over 1. Let's do that right here. So 0 gives me -8. We'll build our function off of 8. What else can I see? I can see that a 2 gets me a 0. Plug in 2, I got 0 over 5, which is equal to 0. Okay, so 2 gets me my x-intercept. 2 might be about here. It's about 1/4 of that, close enough. What else can I see? -1/2. Undefined. Let's go here, -1/2. Okay. Well, anything else? End behavior. Oh, I've got something going up at 4-1, over 1 up 4. I got something going up at 2-1, over 1 up 2. I got something that looks like that, something that looks like that. This is going up faster. Okay? Numerator is going up faster than the denominator, but there's something interesting here. There we go. Let's do there we go. Let's do there appears to be a ratio change here, though. You know what it is? It's 2-1. So this fraction is going to be, when we put in, really big numbers like 1 million. So it's time to actually think just in terms of wealth. 4 times 1 million, the numerator has $4 million to its name. The denominator -8. And the denominator has 2 million plus 1. Generally speaking, I hope we can say how much richer the numerator is than the denominator. I would say twice as rich. So, once again, the exponents were the same, and it appears to have something to do with the division of the coefficients. In the last problem, we had this situation. We had x to the 1, and x to the 1 in the denominator. Well, A and B are the same, 1-1. We had a 1-1 ratio. As these numbers changed, the fraction was following a 1-1 guide. This one's following a 2-1. That's what I can say. See that? Immediately. And it's kind of like a frame when you're pouring cement. All right, here we go again. Another function. What can I see? I can see that 2-1 ratio again because the exponents are the same. So I can immediately go y equals 2. Y equals 2. I can immediately see what I get if I put a 0 in. Hope you can. 18/10. 9/5. 0, 9/5. 9/5 is less than 2. Very important to know that. I've got to do a little work to solve for the zeros here. All right, and that's not part 1 of this video. So that's what I see immediately. All right, and now I'm going to erase the board and make a part 2 later today, in which I start talking about what happens when let's come back to one that's easier to see. What happens when I pick numbers not that this is the most friendly, near -1/2. Might be better to talk about decimals right now, near -0.5. What would happen if I put -0.499999999 in there? Okay, well, that's what we're gonna explore in part 2. All right, so I'm gonna stop this at this point and upload it.